which in some respect led to, inspired many of these models. That is, that symmetry leads to observed quantity. Now, you all know this, but you're so used to it that you forget that it's not obvious. That the translational invariance leads to conservational momentum. Rotational invariance leads to angular momentum conservation. It's so common. Okay. So for example, it's so common now that if we see something that looks to be conserved, that we then look for the symmetry that must be involved. But there's something else so one of the ways we can talk about this in quantum mechanics is, and those of you who actually know group theory better than me will forgive me because I'm going to talk in a very, very naive and simple fashion, and when I make mistakes, you're welcome to take me aside afterwards and gently correct me, or roughly correct me if you feel I deserve it. But the way we look at this is that if we have a Hamiltonian which commutes with generators or the Casimirs, that we can then rewrite the Hamiltonian in block diagonal form. And so we have these blocks which are basically marked out by the irreps of the symmetry group, and they don't talk to each other. And I'm going to come back to this little picture later on. But there's also a mystery. I'm going to try to provoke you a little bit and claim that there's a mystery that we don't think about too much, which is the fact that not only does symmetry lead to conservation laws, but if you look at what's the ground state, the ground state is almost always the most symmetric array, and usually one of the low-dimensional groups. And we don't really think about that. So we see that, for example, if we have translational invariance.